Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Hi, welcome back to Lecture 6 in the Fundamentals of Mathematics. The Fundamental Theorem of Arithmetic. That's what we're going to talk about today. Let's begin, however, by considering 12 divided by 3. Who can tell me what 12 divided by 3 is?
4.
4. That's correct. And that means that 4 times 3 is equal to 12. 4 times 3 is one factorization of 12. That means breaking a number like 12 up into one or two or more factors, okay? In this case, 4 times 3. Is it unique, though? Well, let's see. What is 12 divided by, I don't know, let's say 2. What is 12 divided by 2?
6.
6. Which means that 6 times 2 is equal to 12. That's another factorization of 12. So we see that 4 times 3 is not a unique factorization of 12, is it? So is it possible to have a unique factorization? So first, let me point out that these numbers, 2 and 6 and 3 and 4, we can call them, sometimes we'll call them factors of 12. Sometimes we'll call them divisors of 12. That means that they will divide 12 evenly, right? Remember what dividing evenly means, right? So if I take, 10 divided by 5, 2, with no remainder, right? But what if I did 11 divided by 5?
2 remainder 1.
2 remainder 1. It'd have a remainder. So 5 does not divide 11 evenly. It has a remainder. Therefore, 5 is not a factor of 11. You see? So regarding this issue of unique factorization, the Fundamental Theorem of Arithmetic tells us that there is a unique factorization for every number, every whole number. Okay? Another way to say that is every positive integer. We haven't really talked about integers, so I'm just going to say every whole number greater than 1. And this unique factorization is a product of prime numbers. So the question, of course, now is what exactly is a prime number? Prime number. A number is prime if it is divisible by only 1 and itself. The first prime number is 2. 1, for a variety of reasons, largely in that it divides every number, is not considered a prime number. It would also kill the unique factorization property of the Fundamental Theorem of Arithmetic if we allowed 1 to be considered a prime. So for that reason, 2 is we consider our first prime. Can anyone think of what the second prime number is? The second prime number is 3. And now so far I've made no attempt to demonstrate why 3 is a prime. But let it just be said that if you think about it, there's only two numbers that divide 3. 1 divides 3, right? 1 goes into 3 times, and 3 divides 3. 3 divided by 3 is equal to 1, okay? What about 4? Is 4 a prime number?
No.
No, it's not, because 4 has a divisor of 2. 2 times 2 is 4. Therefore, since 2 is neither 1 nor is it 4, therefore 4 is not a prime number. 5, however, is a prime number, okay? And after 5, the next prime we would find is 7. And after 7, what do you think the next prime number is after 7?
9.
9? 9 is divisible by 3, isn't it? 3 times 3 is 9? Yeah, 11. 11 is the next prime number. And so the first few primes, just write them down here. After 11, we would have 13. 15 is not prime because 3 times 5. Neither is 14 because of 7 times 2. 16 is 8 times 2. 19, however, or did I totally skip 17? I skipped 17, didn't I?
Yes.
17 has no divisors other than 17 and 1, so it's prime. 19 also is prime. The next one after that would be 23. And we go so on and so forth. And we'll talk a little bit more about prime numbers when we talk about divisibility in the next lecture. But for now, if you just remember these primes, then it will get you through today's lecture anyways. So here are the first several primes. If I were to write out a whole bunch of primes, like up to 100 or up to 1,000 or up to 1,000,000, you would observe that there is no noticeable pattern, okay? Like the distance between one prime, like here, 2 and 3, they're separated, they're right next to each other, right? They're neighbor numbers, if you want to call it that, right? Whereas 3 and 5 differ by a spacing of 2. The same as 5 and 7, right? They also differ by a spacing of 2. But what's the distance between 7 and 11? That means what is 11 minus 7?
4.
4, right? And so you'll see that the spacing, there's no pattern to it, okay? At least no observable or easily observable pattern. And so for that reason, the predictability of primes is a very difficult thing. And in fact, if it wasn't so, if it was easy to predict the next prime number, then the whole world's financial institutions would collapse because they're highly dependent upon something called encryption. That's how your credit card number can be sent across the internet or across a telephone wire or through the airwaves, and it's not possible for people to intercept that data that you're sending and get your credit card number so that they can make their own charges on your credit card, because the information is encrypted. It is hidden by the fact that very large prime numbers are hard to discern, and if they were not, if there was an easy way to do it, then you wouldn't be able to use credit cards on the internet or bank account numbers on the internet or passwords or anything like that. So it's a good thing this is a hard problem. It would take a very large computer and you basically have to almost guess. Try every possible divisor and see. But again, we'll talk about primes a little bit more in as far as how do we tell if a number is prime when we talk about divisibility in the next lecture. But I want to finish up with this 12 that we had here, right? I want to show you that there is, in fact, a unique factorization of 12, and I'll show you what it is. And it's unique up to the ordering of the factors, but if we agree we'll always order the factors from lowest to smallest, then the factorization is complete. And so let me show you how to do that. And it's called a factor tree, okay? And a factor tree, we start by writing the number we would like to factor, and then we create a little branching like this, okay? And we'll start with the lowest prime that we can think of, in this case 2. And we'll try to divide 2 into 12. Now we know that 2 goes into 12 6 times, so we'll write this, a 2 and a 6. Now since 2 is prime, I'm going to circle it, okay? And you'll see why in just a minute. I don't consider nodes that are circled because they're prime, and therefore they'll have no factorization other than 1 and the number itself, but we don't include that in the factor tree. So we move on to 6, and we can factor that. So we're just doing exactly what we did for 12, but we're doing it for 6, and we start again at the smallest prime number, 2. That is if 2 divides 6, and it does, because 2 times 3 is 6, and so we write a 3 right here. But 3 is a prime number, so we circle it as well. When we get to the point where we have all of our nodes in our tree, or leaves, whatever you want to call them, circled, then we stop. We're done. And that means that 12 can be written as 2 times 2 times 3. And if we look at that, we'll see the other divisors that we had from before, because we see that 2 times 2, well, that's 4, right? 4 times 3 is 12, okay? We see 2 times 3 right here, right? That's 6. 2 times 6 is 12. Okay? So you have to consider all the different combinations of these factors, these prime factorizations that we have, these prime factors that we have, and that would give you all the possible divisors. Now that's a question in and of itself, and we're not going to consider that, how to generate all possible divisors. But it is a question that in mathematics you can cover. But this is the prime factorization for 12. It is unique. There is no other way to write this factorization in terms of primes other than that right there. Okay, let's try a slightly harder problem. Okay, I'd like you to try doing a factor tree on the number 24. So pause the video and come back when you get that done. So our first step in factoring this is to write our little branching, and we'll start with the lowest prime number, which is 2. And does 2 go into 24? Well, we can use the techniques from the last lecture on long division to try and divide 2 into 24. 2 goes into 2 one time. 1 times 2 is 2. 2 minus 2 is 0. Drop down the next digit. 2 goes into 4 two times. 2 times 2 is 4. 4 minus 4 is 0, so we have a 0 remainder, so we evenly divided 24 by 2, and it's 12. So we write 2 here, 12 here, because 2 times 12 is 24. But 2 is prime, so we circle it. Now we have a problem of 12. Now we saw that in the earlier example. We already did a prime factorization of 12. We know that 2 goes into it 6 times, and 2 goes into 6 3 times, and then we have all of our nodes in our branch structure here are circled, meaning that they are prime, and so we are done with our factorization. So we can write our factorization, or our prime factorization, as 2 times 2 times 2 times 3. Let me work out a slightly harder factorization. 1,155. Where do we begin? Well, we begin by trying to factor it with a 2. So we'll create our branching nodes here, and we'll consider 2 as a factor. So we'll try to divide 2 into 1,155. Well, 2 will go into 11 5 times. 5 times 2 is 10, leaving a remainder of 1. Drop down the next digit. 2 goes into 15 7 times, because 7 times 2 is 14, and 15 minus 14 is 1. Drop down the next digit. We get 15 again, so we know where this is going, right? Still 7. 7 times 2 is 14. 15 minus 14 is 1, so we have a remainder of 1. So 2 will not divide 1,155. So we try the next prime number, 3. 3 will go into 11 3 times. 3 times 3 is 9. 11 minus 9 is 2. Drop down the next digit. 3 goes into 25 8 times. 8 times 3 is 24. 25 minus 24 is 1. Drop down the next digit. 3 goes into 15 5 times, because 5 times 3 is 15. And 15 minus 15 is 0, so we have 0 remainder, which means that 3 divides 1,155. So our first entry in our tree is 3, which we'll circle because it's prime. And the next part of the node is 385, because 385 times 3 is 1,155. And so now we move on to 385. And I'll just give you I'll call it a pro tip. If 2 did not divide 1,155, then it's not going to divide 385 either. Okay, so once you've tried 2 and it failed, you don't need to try it again. All right, so we'll start this by dividing 3. So we create our branches, and we try to divide 3 into 385. 3 goes into 3 one time. 1 times 3 is 3. 3 minus 3 is 0. Drop down the next digit. 3 goes into 8 2 times. 2 times 3 is 6. 8 minus 6 is 2. Drop down the next digit, 5. 25. Well, we know that 3 does not go into 25 evenly, because 8 times 3 is 24. We'll have a remainder of 1. So we're going to have to try the next prime digit. And the next prime number is 5. So let's try dividing 5 into 385. 5 goes into 38 7 times. 7 times 5 is 35. 8 minus 5 is 3. Drop down the next digit. We get 35. 5 goes into 35 7 times. 7 times 5 is 35. 35 minus 35 is 0. We have a remainder of 0. So 5 divides 385 evenly. So we write 5 and 77, because 77 times 5 is 385. That's the relationship in these branches of the tree and the central node from which they emanate. These are factors of the number above it, you see? 5 is prime, so there's nothing we can do with that node, but 77, we don't know if it's prime or not, but let's assume that it's not, and let's see if we can divide something into it. Does anyone recognize something that might divide into 77? Well, if we don't know, we could try dividing 5 into it, okay? Because it worked in the last step. So let's try it in this step. 5 into 77. 5 goes into 7 one time. 1 times 5 is 5. 7 minus 5 is 2. Drop down the next digit. We get 27. Well, 5 times 5 is 25, and 5 times 6 is 30. So there's nothing we can multiply 5 by to get 27. So we have to try the next prime number. After 5, the next prime number is 7, yes? So let's try dividing 7 into 77. Well, 7 goes into 7 one time. 1 times 7 is 7. 7 minus 7 is 0. Drop down the next digit. 7 goes into 7 one time. 1 times 7 is 7. 7 minus 7 is 0. So we have a remainder of 0, and we get 7 times 11 is 77. So we write the 7 here. It's prime, so we circle it. We write the 11 here, because 11 times 7 is 77. But 11, we might remember, was a prime number also, right? So we circle that. And there we have all the nodes are primes, which means we're done with our factorization. So we can write the factorization of 1,155 uniquely as 3 times 5 times 7 times 11. Okay, I would like you to try at home creating a factor tree for 441. So go ahead and pause the video and come back when you've got that one done. Okay, 441. Well, start with our very first branch, and we'll start with the lowest prime number, 2. So we try to divide 2 into 441. 2 goes into 4 2 times. 2 times 2 is 4. 4 minus 4 is 0. Drop down the next digit. 2 goes into 4 again 2 times. 2 times 4 is 4. 4 minus 4 is 0. Drop down the next digit. 2 goes into 1 0 times. We cannot divide 2 into 1. And so therefore we have a remainder of 220, right? As it goes in 0 times. 2 times 0 is 0. 1 minus 0 is 1. 220 with a remainder of 1. So we'll have to start with our next prime, 3. So 3 divided into 441. 3 goes into 4 one time. 1 times 3 is 3. 4 minus 3 is 1. Drop down the next digit. 3 goes into 14 4 times. 4 times 3 is 12. 14 minus 12 is 2. Drop down the next digit. 3 goes into 21 7 times, because 7 times 3 is 21. 21 minus 21 is 0. So we see that 3 evenly divides 441. So we write a 3 here. We circle it because it's prime. And we put 147 in this branch of the tree. Again, there's no reason to try dividing 2 into this because it didn't work in 441. Okay, so we need to start with 3 again. So we divide 3 into 147. Well, 3 goes into 14 4 times. 4 times 3 is 12. 14 minus 12 is 2. Drop down the next digit. 3 goes into 27 9 times, because 9 times 3 is 27. And 27 minus 27 is 0. So it evenly divides 147. So we can get another 3 in our factor tree. It goes into it 49 times. So now we'll try factoring 49. So we create another branch in our tree. We'll start with 3. 3 goes into 4 one time. 1 times 3 is 3. 4 minus 3 is 1. Drop down the next digit. 3 does not divide 19. So we cannot divide this by 3. So that means we need to bump up and try the next prime number, which is 5. So 5 dividing 49. Well, 5 does not go into 4, and 5 times 10 is 50, and 5 times 9 is 45, so we cannot divide 49 evenly by 5. So now we need to go to the next prime number, which is 7. Now, does anyone recognize a factor of 7 that goes into 49? One of our multiplication facts was 7 times something equals 49. Does anyone remember what that is? 7 times 7 is 49. So a 7 here and a 7 here, they're both prime. So we see that we're done, because all of the nodes, or all of the branches of our tree, terminate with the prime numbers, which means that the prime factorization for 441 is 3 times 3 times 7 times 7. All right, next I want to talk about something called the greatest common divisor, often written as GCD. So I'll write GCD, greatest common divisor. So how does that work? Well, you can ask for the greatest common divisor of 2 or more numbers. We're going to focus on finding the greatest common divisor for only 2 numbers. So for example, let's consider a problem, the greatest common divisor of 12 and 18. Okay, and so one way that you could do this, right, is you could simply write down all the divisors of 12 and all the divisors of 18 and pick the one that is common to both, that is also the greatest that is common to both. So let's just see how that would work. We'll make a little table here. Here we'll put the divisors of 12, and here we'll put the divisors of 18. And so let's list some divisors for 12, kind of in increasing order. We know that 2 divides 12, because 2 times 6 is 12. We know that 3 divides 12, because 3 times 4 is 12. We know that 4 divides 12, because 4 times 3 is 12. We know that 6 divides 12, because 6 times 2 is 12. Anything else in here? I could have included 1, because 1 divides 12, and I could have included 12 itself. Okay, and I probably should have. Let me just insert that here. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, they do not divide 12, but 12 does divide 12, because 12 divided by 12 is 1. So now we have all the factors of 12, right? And when we get into divisibility in the next lecture, we'll talk about, well, you might observe that you don't really ever need to go beyond half of 12, right? Because once you found half of 12, there are no numbers that are bigger that are going to divide it, right? So, and you certainly don't need to try any numbers that are bigger than 12, right? Because by definition, they're not going to divide it. But let's do 18 now. Just like every other number, it also has a divisor of 1. It also has a divisor of 2, because 2 times 9 is 18. So you see that 2 is a divisor that these guys share in common. But is it the greatest common divisor? Well, let's see. What else divides 18? Does 3 divide 18? Can you think of anything times 3 that's 18? What about 3 times 6?
Yeah.
That's 18. So 3, another common divisor. So you see these two share this divisor. But is it the greatest? Well, we have to go on. 4. Does 4 divide 18? Let's think. 4 times 4 is 16, and 4 times 5 is 20. So no, it completely jumps over 18. So 4 does not divide 18. What about 5? No. Well, 5 times 3 is 15. 5 times 4 is 20. So no, that doesn't divide it. What about 6?
Yes.
6 does, because we said, 3 times 6 was 18. So 6 times 3 is 18. So 6 does. What about 7? Well, 7 times 2 is 14. 7 times 3 is 21. So no, it jumps over it. What about 8? 8 times 2 is 16, 8 times 3 is 24, so it also jumps over 18. What about 9?
Yep.
Yeah, 9 times 2 is 18, so we put a 9 right there, right? And once we get to whatever number we double, right, that means we're at the end of our divisor list. The only thing that would remain is 18 itself, okay? So there are all the divisors of 12 and 18. We see the ones that are in common. Let's underline them. 2, 2, and I'm not going to underline 1, okay, because that's true for any pair of numbers. 3 and 3 they have in common. They do not have 4 and 6. They do not have 4 in common, but they do have 6 in common, so I'll underline that. And after that, nothing left, right? So which one is the greatest? Well, that would be the 6's, right? So the greatest common divisor of 12 and 18 must be 6. This, however, would be a very slow way of coming up with the greatest common divisor for a couple of numbers, okay? Let me show you an easier way that's A, a little more systematic, and B, a little faster. I'll leave this up for now, but I'm going to write this factor tree over here. So I want to create a factor tree of 12, which we've already done, so I'm just going to write it up really quickly. We remember that it had 2 times 6, which had 2 times 3, and so 12 factored as 2 times 2 times 3. What about 18? I don't think we've done that yet, so let's write the factor tree for 18. 18 has 2 times 9. 9 factors as 3 times 3. And we seem to be done because everything is circled, so we get 2 times 3 times 3, the unique factorization for 18. So the way to construct a greatest common divisor, this is the trick, so to speak. So I'll write GCD of 12 and 18. We look through the factor tree here, right, and we put things in that it shares in common. So they both share a single 2 in common. So I'm going to put a 2 in this, okay? Do they share 2 2's in common? No, they do not. So I'm not going to write another 2 in there. But they do have a 3 that they share. So I'm going to write a 3 in here. And so I get that 2 times 3 equals 6. And that is my greatest common divisor. Okay? So you put numbers in that they have in common one at a time. If they had 2 2's in common, we would have put 2 times 2 in here, but they don't. So you just start at the tree and you go, does it have a 2 in common? Yes, it does. I put that 2 in. Move down to the next node. Does it have another 2? No, it does not. We already have the 2 that it has. So we move to the next node. Does it have a 3? Yes, it does. It has 1 3. So we put that 3 in and we're done. Okay? So that's how you walk through and you get the greatest common divisor. Let me give you one to try. I'd like you to compute the greatest common divisor of 36 and 60 using a factor tree method. Do that now. Pause the video. Come back when you've got it done. All right, so we'll write our kind of our cumulative answer down here, the greatest common divisor of 36 and 60. The first thing we have to do is we have to factor 36 and 60 using the prime factorization methods we learned. So we'll write 36 here. We'll start with 2. Does 2 divide 36? Well, let's see. 2 into 36. 2 goes into 3 one time. 1 times 2 is 2. 3 minus 2 is 1. Drop down the next digit. 2 goes into 16. Well, 8 times 2 is 16, so 8 times with a remainder of 0. So yes, it does. So we'll write our first entry as 2, which is a prime, times 18. Now we have to factor 18. We just did that. It's right here. So we can just copy on over from here the factorization that we got before. That's 2 times 9, which is 3 times 3. And so 36 is 2 times 2 times 3 times 3. Now let's do 60. Well, 60, we'll try dividing 2 into 60. 2 goes into 60. Well, 2 goes into 6 3 times. 3 times 2 is 6. 6 minus 6 is 0. Drop down the next digit. How many times does 2 go into 0? Well, 0 times, right? 0 times 2 is 0, so there's no remainder, so we can't evenly divide 60 by 2. So we write 2 and 30 right here. Now we just repeat that procedure, this time for 30. Let's try 2 again. 2 into 30. Well, 2 goes into 3 one time. 1 times 2 is 2. 3 minus 2 is 1. Drop down the next digit. How many times does 2 go into 10? Well, 5 times 2 is 10, so 5 times, leaving us a remainder of 0, so we can get 2 and 15. Now we have to try and factor 15. So we start with the lowest prime again, still 2. Try to divide 2 into 15. And this one we can just think about it, right? Because 7 times 2 is 14, 8 times 2 is 16, so 2 definitely does not divide 15 evenly, which means we're going to go up to 3. Let's try 3. I should put my branches here. Can we get 3 into 15? This one I think we can do just with multiplication facts, right? Because 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15, which is what we're looking for. So 3 is a factor, 3 times 5. But 5 is also a prime, which means that we've finished our factorization of 60. So we can write this as 2 times 2 times 3 times 5. That is its unique prime factorization. So now to construct the greatest common divisor, we'll start here. Do we have a 2 in common? Yes, we do. So we'll put that 2 in. Then we move on to the next factor. Do we have another 2 in common? Yes, we do. So we'll put that one in as well. Now we move on to the next factor. 3. Do we have a 3? Yes, we do. So we put that in also. Then we move to the next factor. Do we have another 3? No, we do not. We only have the one 3. So there are no more factors we can put in. Okay, so you see that excluded from this is the 5 and the additional 3 from here, right? So our greatest common divisor of 36 and 60 is, well, 2 times 3 is 6 times 2 is 12. Alternatively, you could have done 2 times 2 is 4 times 3 is 12. Doesn't matter. It's 12. So the greatest common divisor of 36 and 60 is 12. Now I want to move on to a related topic called the least common multiple. So the least common multiple is the smallest possible whole number that is a multiple of two given numbers. And if you think of a simple example of like 4 and 8, right? Well, 4, multiples of 4, you have 4 times 1 is 4. Obviously, there's nothing you can multiply 8 times to get 4. 4 times 2 is 8, but 8 times 1 is 8. So you see that 8 is the least common multiple of 4 and 8, right? That's a kind of a simple example. I'm going to show you the procedure using the same prime factorization techniques we showed here for finding the least common multiple using these factor trees. And so let's consider the least common multiple of 12 and 18. It's a very similar procedure, but there are some unique differences, right? Remember, whatever this multiple is, it needs to be divisible by both 12 and 18, right? So everything in these numbers has to be in there, yes? Does that make sense? So for example, if these were a couple of prime numbers, then the least common multiple would simply be the product of those two primes. But the general procedure that I like to use anyways is I'll always write the numbers in this order. It doesn't matter what order you write them in, but I'll always write them in order from smallest to largest. And so we begin by putting all the factors of 12 in this answer for the least common multiple. So I'm going to put 2 times 2 times 3 in there already, okay? That's where I'm going to start. 2 times 2 times 3, because that is all of the factors of 12. Because whatever this number is, whatever this least common multiple is, it needs to be divisible by 12, right? But it also needs to be divisible by 18. So we needed all of these factors in there. But if we look, we see we already have some, right? We already have a 2, which we need. We already have a 3, which we need. But we also need another 3. So we're going to put one more 3 in here, times 3, right? And so this is going to get, since this is 12, 12 times 3 is, anyone do that? Well, we can always try it like this. 12 times 3. Well, 3 times 2 is 6. 3 times 1 is 3. So 12 times 3 is 36. So this is equal to 36. So the least common multiple of 12 and 18 is 36, right? And we can see what that is, right? Because we see that 12 times 3 is 36, right? What about 18? Well, that would be 3 times 3 times 2, right? This part here. So that's 2 times 18 is 36. You see? Least common multiple. Now I want you to try at home the least common multiple of 36 and 60, which you can take advantage of the fact that we've already done the factorization here to solve that. So go ahead and pause the video, try to put together the least common multiple at home. So again, I would put in all the factors from at least one of these two numbers. I usually start with the smallest one, so 36. So I'll put in 2 times 2 times 3 times 3. That is 36. And that needs to be one of the factors in the least common multiple. So we've got that in. Now we need to put in all the factors from this number, 60. But we don't want to double count. We don't want to put in, we already have a 2 in here, so we don't need to put another 2 in here. This second 2 is also already in here. The 3, that's also in here. But we need a 5, and we don't already have a 5, so we have to put in a 5. And so what do we have? We've got 36 times 5 is the least common multiple of 36 and 60. So we can figure that out by simply multiplying 36 times 5. 6 times 5 is 30, carry the 3. 5 times 3 is 15, plus 3 would be 18. And so we get an answer of 180. And we can see that 36 times 5 is 180. That's the multiple of 36. It's the fifth multiple of 36 that's common, that's smallest. And if we group these together, we get the 5 times the 3 times the 2 times the 2. That's going to be 60 times 2 is 100. No, that's not right. 60 times 3, sorry. Yeah, we got 5 times the 3 times the 2 times the 2. It left 1 3 out, right? So that's 60 times 3 is the 180, right? That's the least common multiple and the greatest common divisor. This will prove very useful when we deal with fractions. But let me show an interesting connection as we close out the lecture between these two quantities, the greatest common divisor and the least common multiple. So the interesting relationship is that the least common multiple of a comma b is equal to the product of a times b divided by the greatest common divisor of a and b. And vice versa, right? It's also true that we can also write that the greatest common divisor of a and b is equal to the product of a times b divided by the least common multiple of a and b. And so we can test that out here. So first we need to get the products a times b. So we'll do the easy example here. We'll use the greatest common divisor of 12 and 18, right? So if we substitute in here, least common multiple of 12 and 18 is going to be equal to the product of 12 times 18 divided by the greatest common divisor of 12 and 18. Okay, so 12 times 18, that one we have to do. So let's multiply that out. 18 times 12. 8 times 2 is 16. We carry the 1. 2 times 1 is 2, plus 1 is 3. Don't forget to put a 0 here because we're multiplying tens now. 1 10 times 8 is 8 tens, or we'll put just an 8 here. 1 times 1 is 1. Add this up. That's 6 plus 0 is 6. 8 plus 3 is 11. Carry the 1. 1 plus 1 is 2. 216. So this is equal to 216 divided by, well, the greatest common divisor of 12 and 18, which we already did. We got that right here. The greatest common divisor of 12 and 18 is 6. So this is divided by 6. And so now we have to do this long division problem. We'll divide 6 into 216. 2 goes into 21 3 times. 3 times 6 is 18. 21 minus 18 is 3. Drop down the next digit, 6. How many times does 6 go into 36? What's 6? 6 times 3 is 36. 36 minus 36 is 0, so no remainder. So we see that 216 divided by 6 is 36. And that is exactly what we calculated as our least common multiple using the factor tree method, yes? And I will leave it to you to try on your own that this formula works. You could have calculated the greatest common divisor. That would have been 216 divided by 36. Right, you should get 6, and you can, of course, you can try it on this as well to see that it works. But it's a fundamental relationship between the two, that the least common multiple times the greatest common divisor is equal to a times b. That's another way to say this. I'm going to write that last way here. This is all hinged upon the idea that the least common multiple of a and b times the greatest common divisor of a and b is equal to the product of a times b. And all of this is because of the fundamental theorem of arithmetic. Now, I know these techniques and this stuff seems kind of obscure, right? It will prove very useful, though, when we get to fractions and we're trying to deal with fractions. And you'll see it come into play then. It's not a hard skill to get doing these prime factorizations. It's a very useful skill, though. It's going to turn out to be a very useful thing. And it's an interesting thing, too, right? A lot of people like to say that, the numbers, prime numbers are like atoms. And what do you get when you put atoms together? You get molecules. Well, what are the molecules? We call them, so if a number is not prime, by the way, we call it a composite number. Think of the word composition, or composed of. It means it's composed of stuff. Prime means it's like primal, right? It's the stuff that can't be broken down, okay? So the prime numbers are like atoms, and the composite numbers are like molecules. You see? So the quality or the character of a number is given to it by the primes of which it's composed. And this will turn out to be important in our discussion of divisibility, which we'll get to next time in the next lecture. I'll see you then.